You got this. In the past unit, we explored vectors, lines, and planes in 3 dimensions. Today, we're going to talk about functions in 3 dimensions. And what you're going to discover today is that many of the properties from 2 dimensions will still be true. You might remember a function in 2 dimensions would be y is a function of x. When we talk about multiple variables, we just switch the notation a little bit. Instead of saying y is a function of x, we're going to say z is a function of x and y. And just like in a function where this says for every x is exactly 1 y, this says for every x and y, x and y, there is exactly 1 z. Right there. And the other thing that I want you guys to hopefully notice is that in this case, both x and y are independent. So we actually are going to have independent. There we go. Can't spell today. So we are actually going to have 2 independent variables, or even more later on. So it is read z is a function of x and y. Just like whereas y is a function of x, they're just saying z is a function of x and y. We're going to start with the equation of this plane, and we want to convert it into our function form. Well, the first thing we're going to do is we solve for z. Just solve for z. We would get z equals 7 minus x plus 2y. And then I already have it. Z we know is a function of x and y, so I'm going to go f of xy is equal to 7 minus x plus 2y. And there is our function form. So let's look at the next one. We want to write the equation of a plane with the normal norm 3i 2j plus k going through the point 1, 0, 1. So we want to write the equation of a plane, and we're going to write. So we should remember this from the last unit because this is normal. We know that this is going to be perpendicular to the plane, and that gives us our ABC, right? Our ABC. So when I write my equation, we're going to go 3 times x minus 1 plus 2 y minus my point 0 plus 1 z minus 1 equals 0. Now if you forgot how to write the equation of a plane, take a look at one of my other videos from the last unit. If I were to simplify this, we would get 3x minus 3 plus 2y plus z minus 1 equals 0, or 3x plus 2y plus z equal to 4. And so there's the equation of our plane. Well, let's convert this to function notation. So we're just basically going to again solve for z would equal 4 minus 3x minus 2y. Therefore, our in function notation, in terms of a function in terms of x and y, we would get 4 minus 3x minus 2y. It's the same thing. We just replace z. Now, words kind of used. Remember, a plane. You all remember the vertical line test, right? Right. Remember, it says if you have a function that graphs any past the vertical line, we get a function. Well, a plane is a function also, but in this case, we're talking about the change in z's. If we cross the z more than once, it's not a function. So every plane will be a function. And that's what this is kind of telling us right here. That this is a function. That for every x and y, there's exactly 1 z value. It's kind of like our vertical line test. Number 3, given that the function g of xy is the equation of the plane, find the norm of the function. So, okay, there's the equation of my plane. We want the norm. So remember, norm is going to be the perpendicular vector to the plane. So in my plane where we have g of xy equal to x minus 5y plus 2, I want to write this in my normal notation, non-function notation. So remember, g of xy, that's just z really, equals x minus 5y plus 2. And if I were to solve this, we would get x minus 5y minus z equal to negative 2. So there's our plane, not in function notation, but in our standard notation. To get the norm, remember the norm is always going to be perpendicular to the plane. So it's going to be looking at your A, your B, your C, right? Looking at your A, your B, and your C values, our norm would be 1, negative 5, negative 1. Now, let's say you solved it differently. You brought the x and the y over, and you left this as a positive 2. Well, then your norm would be negative 1, positive 5, positive 1. There would be a norm. Now, if you want to write this in your ijk, I minus 5j minus k, or negative I plus 5j plus k would also work. So you can write in the other forms as well. Now there would be your norms. Norms. All right, so let's go ahead and start talking about, well, if these are functions, well, how can we find the domain and ranges of these functions with multiple variables? And you're going to find out they're very similar to what you did in Algebra 2 and Pre-Calc. We look for domain restrictions. Well, what are the two things you really can't do? One, you can't divide by negative. No division by a negative. No division by 0. That was stupid of me. No division by 0. And 2, the square root of a negative. These are your no-nos. That's how we find domain restrictions. Those are the only two things really we can't do in math. We can't divide by 0, and we can't take the square even root of a negative. So be careful. At times we will wind up with variables in the domain and range, and this should kind of make sense. And the reason for that is our functions is in two variables. Okay, so when we find the domains, this is the hint I'm going to give you guys. We have two independent variables, and as a result of having two independent variables, the domain will most likely be in terms of x and y. Most likely be in terms of x and y. That's because of our independent variables. It's very similar to what we did back in Algebra 2 and Pre-Calc. If I'm given the function f of x equals the square root of x, well, my domain says x has to be greater than 0, or equal to 0, I suppose. Likewise, well, what if I have something that's the square root of x plus y? So now I have two variables. Well, my rule's the same. This cannot be negative, so therefore we say x plus y has to be greater than or equal to 0. That their sum has to be greater than or equal to 0. So we can do that. Oh, look, there's the first one. All right. So there's our first one. If I'm looking at the function of f of xy equals the square root of x plus y, this is what the graph looks like. By the way, I got these graphs off Desmos 3D. So if I want to find the domain, I just have to remember there are no negative even roots. So no negatives in an even root. So when I'm looking at this, I can take that x plus y. This has to be greater than or equal to 0. That's the easiest way to write it. Sometimes people say, or x is greater than or equal to negative y. That's okay to write it that way too. So if you want to write this in set builder notation, it'll be x, y, all x, y, such that x plus y is greater than 0 or equal to 0. Very easy to do. Let's go ahead and calculate the range. To get the range of our graph, well, we think about, well, what's the smallest this can be? I always tell people, to get the range, what's the smallest value? So my smallest value that this could be was, well, this will never be negative. Matter of fact, the smallest it can be is if both x and y were 0. So that's what they're saying. X plus y is greater than or equal to 0. So my smallest value is going to be 0. My largest value? Well, sky's the limit. X and y can be any number positive, so that goes to infinity. So my range will be from everything, all z, such that z is greater than or equal to 0. Now, if you just say z is greater than 0, I'm okay with that. If you just say x plus y is greater than or equal to 0, that's okay too. All right. Like I said, because we have two variables, our domain most likely is in terms of x and y. It's not as simple as it was earlier. It's not as simple as it was back in pre-calc. So number 5, now we have our function of f of x, y is the square root of x plus the square root of y. Well, let's go ahead and calculate our domain here. Well, the domain here, these are independent from each other. So we're going to solve these independently. So we would say x has to be greater than or equal to 0 and y has to be greater than or equal to 0. There's our domain. And again, you can write that in set builder notation. You can say all x, y such that x is greater than or equal to 0 and y is greater than or equal to 0. To get the range, again, these will never make, even if I make x negative, that's not going to make my value negative. So the smallest these can be is 0. So I would get 0 plus 0. So my smallest value is 0. My largest value is, again, infinity, because I can keep adding positive x and y. So my range is, again, just going to be z is greater than or equal to 0. And again, you can write that in set builder notation if you like. All right, go to part 2, and we'll take a look at a few more examples.